All right, welcome back. In our next section, part of our CCNP Enterprise Core discussion here, we're going to talk about understanding Cisco switching paths. What does that mean? Well, that means how does a switch work, right? How does a switch make forwarding decisions? Not, we know that switches do MAC address learning and they make decisions based on a layer 2 frame, right? But we'll talk about different switching methods, like what is store and forward switching, what is cut-through switching, what is fragment-free. We'll talk about Cisco Express forwarding and how that allows the switch to do hardware-based forwarding as opposed to software-based forwarding and so on. So that's what we're looking at in this particular section here. The idea is that we're trying to do much faster processing of the frames using something called content addressable memory, or the CAM table, which basically is just a fancy term for describing the MAC address table, right? Kind of interesting that it's, MAC backwards, but yeah, that's the idea. We're trying to get data into a switch port and out of a switch port as quickly as possible. Now, we're not talking about all the other features here. We're not talking about VLANs and implementing 802.1x and other layer 2 functions that might be extended to the switch. What we're focusing on in this case is just the basic switching operations, right? And that's what our goal is. So traditionally, when we have a switch, it's a layer 2 device. It works at the data link layer of the OSI model, which means it makes its primary forwarding decisions based on layer 2 addresses, which are MAC addresses. Now keep in mind, guys, that this is a really basic topic, right? It's like CCNA 101, switching, how does a switch make decisions? But we're going to try and expand on this a little bit and talk a little bit about how we can facilitate more efficient communication with the switch through the use of Cisco Express forwarding and so on, right? Now, traditionally in most layer 2 networks, we implemented something called contention-based access, or specifically CSMA-CD, carrier sense with multiple access and collision detection, which allowed us to identify when we were able to transmit a frame and when we couldn't transmit a frame, or actually you should say bits in this case, right? Because we had shared resources. We had essentially a bus that allowed clients to communicate. And if multiple clients tried to use that bus at the same time, a collision would occur and the data would get corrupted. Now, in most modern network designs, we don't have to worry about this, right? Because not only does the switch operate at layer 2 as opposed to layer 1, it has the ability to do full duplex communication, meaning that we can send and receive at the same time. It also has the ability to buffer large frames or to store frames if multiple frames need to be processed for an individual egress port, and so on. So there's all kinds of ways that we can manage this process. But how did CSMA-CD work? Well, you had a scenario where a collision would occur. Two clients tried to transmit over essentially the same wire, logically the same wire at the same time, and that data literally collided, all right? And what happens in that case? Well, the data gets corrupted. So rather than having the clients continually try to retransmit, we would go into this back off timer. Every client would basically stop transmitting, and they would implement some sort of decremental timer value, and then whomever's timer expired first, they would be the ones that would be allowed to transmit. We don't really consider this to be a huge component of modern switch networks today, though. Because of full duplex communication, because of the way switches handle multiple frames, especially when they're trying to send frames to the same destination with buffering and so on, CSMA-CD doesn't really come into play. It's still, we do have contention-based access that still exists with wireless networks, but we use a different contention scheme in wireless called CSMA-CA, which is collision avoidance, not collision detection. So switches basically learn passively. I always describe a switch as a passive device. It never goes out there and tries to actively identify who's connected to that particular device. The learning component is the CAM table. That's the MAC address table. Notice what's in that CAM table. You've got a MAC address, which identifies the endpoints, the port that those endpoints are attached to, and the VLAN that those ports are a member of, right? The endpoints themselves don't go into VLAN. The port that they're attached to is assigned to a particular VLAN. So this MAC address table stores this information. Initially, that MAC address table is blank, for the most part. There are some well-known MAC addresses that are part of that table automatically, just because the switch is participating in different protocols like CDP and DTP and so on. But for the most part, the table is empty. And the switch will just simply passively wait for frames to pass back and forth. And as those frames pass back and forth, it starts to build this database, this MAC address table database. We know that switches operate at layer 2. Now that doesn't necessarily mean that a switch can't perform functions above layer 2. You can, for example, assign layer 3 access list to a switch port, and it can filter traffic based on layer 3 information. Or even possibly layer 4 information for that matter. We also know that switches can incorporate some sort of routing component, right? You can have routing that's possible on a switch. It's called a multi-layer switch. But functionally and fundamentally, switching is a layer 2 function. And the reason we define it that way is because it is done based on MAC addresses. Media access control addresses are layer 2 addresses that are burned into a device or programmed through software that allow us to identify a device within a layer 2 domain. Now there's only 2 types of decisions that a switch is going to make once it receives a frame. Am I going to forward the frame, or am I going to flood the frame, right? Am I going to forward the frame, or am I going to flood the frame? Well, that decision is going to be made based on what the switch knows. If a switch receives a frame that's destined for host X, and host X does not exist in the database, then that frame is going to be flooded out of every interface except for the interface that it came in on. If the destination is known and it is mapped to a particular port, so say host X is mapped to port 5, then the switch will make a forwarding decision and it will forward the frame out of that interface, port 5, and it will filter that frame out of every other interface. Now there are some scenarios in which frames will get flooded even if a destination is known. It depends. Typically we would see something like that in multicast and so on. All right, so we'll just break down what the book is saying here. It's kind of summarizing what I've already said, but I want to make sure that we don't miss anything here. It says there's no contention on the media. We're in the first paragraph here. Collision domains are limited to each port. Because we're running in full duplex mode, there's really no contention. So we're only checking the frames for errors. We're not necessarily checking to see whether or not we need to delay a frame or whatnot based on contention-based access, because full duplex means I can send and receive at the same time. Second paragraph here, to figure out where a frame must be sent, the switch will look up the MAC address in its MAC address table. This information can be told to the switch, or the switch can learn it automatically. So we can do gratuitous processing of information where I'm basically going to the switch for the sole purpose of telling that switch, hey, I'm here. Or, and this is probably more common, the switch simply just waits for frames to come in. And then based on that frame arriving on a particular port, the switch will then map that particular MAC address to that particular port. All right. The switch listens to incoming frames and checks the source MAC address. If the address is not in the table already, the MAC address, the port, the VLAN, they're going to be recorded in that forwarding table, and that table is stored in what we call content addressable memory, or the CAM table. Now there is a finite amount of space that exists within the cam table itself. And it depends on the switch model, how much memory the switch has, and so on. But there is a limit to how much information can actually be stored. One of the questions I always ask my CCNA students is, what happens if that memory is full? What happens to new entries? The answer to that is nothing. They don't get added. We don't do first in, first out type of scenario. We basically will maintain information in the cam table for 5 minutes. That's the default timer, the aging timer for entries in the cam table. So 300 seconds, we'll store that information. As long as that client is communicating, as long as we're seeing frames from that particular client, not to that client, but from that client, that information will be maintained in the database. And additional entries will not go in if the cam table is full. There's actually a type of attack which is called a cam overflow attack or a MAC flooding attack, where the attacker is trying to turn the switch into a hub by simply filling up the memory with bogus entries, so that legitimate entries can't go into the database, and the switch will start flooding all the information rather than forwarding the information, right? What happens if the destination MAC address of the frame is unknown? Well, we already talked about that, right? The switch is going to flood that frame out of every port within the VLAN. I forgot to mention that previously, right? We don't flood across VLANs. We need routers to send traffic across VLANs. So if a frame arrives on VLAN 10 and the destination MAC address of that frame is unknown, that frame will then be flooded to all of the other interfaces participating in VLAN 10, with the exception of where the frame came from. We never send the frame back out the same interface it came in on, because that would create a looping condition, which would be bad. Okay? Broadcast traffic, multicast traffic, that's going to be flooded by default. Multicast we can manage. If we don't want our multicast traffic to be flooded, we can actually manage that using something called IGMP snooping. Internet Group Messaging Protocol snooping, where the switch will actually monitor the IGMP messages going back and forth between the clients and the routers. And based on that, it will do kind of like a multicast MAC address membership, if you will. So it will flood the multicast traffic only over the interfaces that need to see it. All right. So in the first example, the switch receives a frame on port 1. Now, if I go up to the example here, this is what they're referring to. The destination MAC address in this case is quad 0, quad 0, quad 5. Now, if I reference my database, quad 0, quad 0, quad 5 is on port 5 in VLAN 1. So in this case, I have an entry in the database, so I can make a filtering decision, meaning that I forward the frame out of port 5 and I filter the frame from all of the other ports. This is particularly important. And look, I know you guys know this. This is pretty basic information. I mean, it's almost like pre-CCNA, right? ICND1 type of stuff. But, you know, it doesn't hurt to kind of review it. But we know the switch is going to forward that frame. In the second example, the switch receives a broadcast frame on port 1. We know that's going to be flooded, but only out of the interfaces that are part of the same VLAN, if you will. That's why we call it a broadcast domain. All right? But there is more to a switch than just the CAM table. We have something called Tcam tables, ternary content addressable memory. Ternary, by definition, means a triple or 3, or, you know, you can define it a couple of different ways, but it's usually some sort of quick lookup database or quick lookup table that stores 3 pieces of information. Now we have our layer 2 forwarding table, which is our CAM table. That's our standard MAC address to VLAN to port mapping. We have a Tcam that allows us to store ACL information, and we have a Tcam that allows us to store quality of service information. What is the point of these different tables? Well, the point of these tables is to do processing in hardware using application-specific integrated circuits as opposed to doing processing in software. That's the primary goal of each of these. We want to do our processing in hardware and not software. So let's break down what some of these databases are, right? Obviously, from a standard forwarding decision, the switch is going to look at the CAM table, and it's going to say, look, I received a frame to MAC address X. I need to make a decision. How am I going to process this frame? And this is just a fundamental processing piece. We're not even talking about, am I doing store and forward where I'm doing a CRC check and all that, or am I doing fragment free or cut through? I'm just saying, what's my basic forwarding decision? Should I forward the frame? Should I flood the frame? Should I drop the frame? Because I might have some sort of security component that says you're not allowed to forward this frame. All these decisions are made by these three databases, right? Our layer 2 forwarding table is the index that we use to identify the VLAN, the port, the MAC address, etc. That's what we call a MAC-binded port. The ACL Tcam, or what we call a ternary content addressable memory, is where I identify whether or not I should forward the frame or not, right? Because I might have an access list, which, by the way, would include things like a VLAN filter, a port-based ACL, an access list that might be assigned to an SVI, so more of a traditional layer 3 access list, but some sort of access list that allows us to say that we're filtering traffic, right? And then also the QoS Tcam allows us to identify the QoS properties that are applied to that frame. Is it going to be prioritized? Am I going to do policing or shaping? Is there a classification and marking taking place, and so on? The idea, though, is that we're trying to do all of this in hardware, not software. We want to make sure that we're doing this in hardware, not software. So that's a really, really important element. And it's really something that's kind of unique to, I wouldn't say it's unique to Cisco specifically. There are other vendors that incorporate these types of components, but it is unique in the sense that it's not something you're going to see in like a Netgear switch or a D-Link switch that you might buy at Walmart or Fry's or something like that. The one unique thing that Cisco has, well, I believe Juniper does this as well, but is the ability to program that ASIC functionality on the fly. Most vendors that incorporate the use of hardware forwarding mechanisms, those are pre-programmed and pre-configured hardware forwarding mechanisms that can't be modified. That's where the software-defined piece comes into play. All right. So Cisco switches maintain these different databases. The CAM table, like I said, is used for layer 2 switching. The Tcam for layer 3 switching. That's where QoS and access lists come into play. It's most people, when they think of a switch, they think of the CAM table, right? That's our fundamental layer 2 forwarding mechanism that the switch uses to make its primary forwarding decisions. The Tcam table, ACLs, quality of service, any kind of upper layer processing function for inbound or outbound ACLs, QoS, etc., allows us to do hardware-based forwarding while still maintaining this layer 3 functionality. So the idea here is that we're taking what would normally be control plane processed information, CPU processed information, and we're extending that down to data plane processing so that we get wire speed functionality. All right. All right, let's see the question here, which we'll probably see at the end again anyway. Which table is used by a switch to figure out where a frame must be sent? That is the MAC address table. ARP cache is what allows us to map our IP address to our MAC addresses. Interface table, there's no such thing. Routing table does exist, but that would be obviously for a router. That would traditionally be called a routing information base. That's or control plane routing information that gets extended down to the data plane using Cisco Express forwarding and a FIB, a forwarding information base. All right, folks, welcome to our first discovery in our CCNP ENCORE course. We're going to be taking a look at a very basic discovery in this first one here. We're going to be taking a look at the CAM table, investigating the content addressable memory. Obviously, the CAM table is, based on our discussion that we've had so far, is what we use to verify the information that the switch has learned in the topology, right? Within the, the devices that are either physically connected to the switch or the devices that are connected through maybe a different switch in the topology. We'll be able to identify what port, the addresses, the MAC addresses specifically were learned on, what VLAN that particular port is a member of, and so on. And this allows us to kind of investigate where particular devices exist in the topology. So we've got 5 PCs here, all in the 10.1.1 subnet. We're going to focus primarily on just generating some traffic from PC1 to all the devices on the subnet. So we're going to go into PC1 and we're going to do basically just a broadcast ping. All of our devices are already up and running. I'm going to do a ping to 10.1.1.255. We'll do a repeat count of 10 and I'll just generate some kind of standard Ethernet frames by simulating 1500 byte frames. Now, what's going to happen as I go through this process? Right now, switch 1 doesn't have any information that it's learned because we just turned that switch on and no traffic has been generated. We're going to assume that in this case anyway. So what's going to happen is PC1 is going to start to generate some traffic. It's going to send its ping, and because it is destined to a broadcast address, the corresponding MAC address of that particular frame is all Fs, which means that the traffic is going to be flooded through the network. And then hopefully anybody that's up and running will be able to respond to that information. So we'll go ahead and execute the ping, and we should see some replies from the various hosts within the network. 2, 3, 4, 5. I'm number 1, obviously, so I'm not going to see a response for myself. So what's happening in this case is now the switch is essentially monitoring this traffic flow. And switches are very passive by nature, by the way. They don't actively go out and try to identify who's connected to a particular port. They just simply wait for traffic to flow back and forth. And as traffic flows back and forth, they do one of 2 things. The first thing they need to do is they need to identify whether or not we need to update the contents of the CAM. So if I do a show MAC address table in this case, I can see my CAM table is completely populated. This is the MAC address of the neighboring switch, which is on gig 00. This is the MAC address of PC1, PC2, PC3, PC4, and 5, which are connected to switch 2. So we do have multiple entries on a per port basis. And there's no real limit to that other than how many MAC addresses typically can be assigned to a particular port. That's going to be specific to the platform, right? Depending on what type of platform that you're running in the topology. All right, so we can see that the MAC address table has been populated. Now, how does that happen? Well, as a frame comes into the switch, the first thing that the switch is going to do is say, is the source MAC address of this frame in the database? And if the source MAC address of the frame is not in the database, I make a note of what port that frame came in on, what VLAN that port is associated to, and I update my CAM table with that pertinent information. The next decision that the switch has to make, of course, is how do I forward this frame? Do I forward it to a specific port based on the known destination MAC address, or do I flood it out of every port except for the port that it came in on if the destination MAC address is unknown in the CAM table? So because we did ping that broadcast address, it provided these switches the ability to kind of update their entire database so everything is known. All right, so we see PC1 is mapped to port 1, PC2 is mapped to port 2, PC3 is mapped to port 3, and then we have the 2 other devices that are mapped to gig 00. All right, now it is highly likely actually that in a lot of switches you're going to have thousands and thousands of entries, and you may have to track down a device that might be connected to a particular port. Maybe it's not connected to a port physically on your switch, but maybe a port on another switch. And it might be difficult to kind of parse that information. So there's many ways we can parse this information. I can do a show MAC address table for a specific interface if I choose to, and I can see all the MAC addresses that correspond to that particular interface. I could also use some various parsing commands like a pipe include or a pipe exclude or pipe begin and so on. So the address keyword that we specify allows us to identify the different addresses that exist in the table based on their VLAN membership. How is it possible, by the way, for switch 1 to see multiple MAC addresses through gig 00? Because these MAC address tables are locally significant to the switch. They're not shared from switch to switch. And in this particular case, that MAC address, those two MAC addresses, I should say, actually the 3 MAC addresses, were learned on that particular port. So like I said, it's entirely possible to see. In fact, if I do a show CDP neighbor, I can see switch 2 is connected on gig 00. And that might also be a way that you can kind of walk through the network to be able to eventually identify where a particular client's connected. By walking through that network, you can say, okay, well, these MAC addresses are learned on gig 00. Let me see through CDP what device is connected on gig 00, and then let me go ahead and access that device and kind of run through the same commands. And eventually you get to the device that would have that client directly connected. Now you might not have one physical port that's interconnecting your devices. It could be an ether channel or what we call, maybe it's a LACP or a PAGP ether channel and so on. But the general concept is still the same. Now, CAM tables can hold thousands and thousands of entries. It really depends on the switch type, the switch model, and so on, and how you have your SDM templates assigned and so on. But although that might seem like a lot, in a really, really large enterprise environment, it may not be enough. All right, so if there's 2 ways that we handle that, right? If a MAC address hasn't been heard from for a very long time, that's what we refer to as a stale entry, those are going to be aged out. This is called the global aging timer for the CAM table. The other thing that would happen is MAC addresses would simply not get put into the database. It's kind of a common misconception that we do some kind of first in, first out type of scenario. So the oldest MAC addresses would be overwritten so that the newer MAC addresses would have an opportunity to get updated into the database. But that's actually not the case. If those clients are still communicating, those old MAC address clients are still communicating, or the aging timer hasn't expired, those MAC addresses won't leave the database at all unless you reboot the switch or clear the MAC address table manually. There is a type of attack that exists in networks called a CAM overflow attack or a MAC flooding attack, where the attacker will attach itself to a switch and start flooding the switch with a bunch of random bogus MAC address entries. And the goal of that is to turn that switch into a hub. Because if I can fill up the MAC address table with a bunch of bogus entries, the legitimate entries won't have the ability to go into the database. So unless these MAC addresses age out, the switch is just going to fill up the MAC address table with all these old entries, and the new entries can't go in, and that in turn will turn that switch into a hub. Now there are ways we can protect against this by using things like port security, and we can also do other layer 2 protection things like dynamic ARP inspection if somebody's trying to spoof somebody's MAC address or poison ARP entries and so on. So let's see what the MAC aging time is in this particular switch. If we do just MAC address table aging time, and we can see the aging time is 300 seconds. Now typically that's pretty sufficient for most networks. We don't usually want to change that. But there are scenarios where you may consider changing that value. For example, the default aging time for the address resolution protocol for those entries is 4 hours, for Cisco anyway. In networks where you have hosts that don't generate a lot of traffic for long periods of time, you can have your CAM table entries time out every 5 minutes. So we might have some lack of synergy there, And in those cases, we might have an increase in the amount of flooding of traffic because the MAC addresses are not known, but the ARP entries are still active. So we're not doing any kind of discovery, which means that MAC address tables aren't getting updated. We also can't summarize CAM tables like we can summarize things like routing tables. So if I have 1,000 devices in my network, that means I'm going to have 1,000 addresses per CAM table on the switch, per switch. So when the CAM table gets full, like I said, unless those entries age out, the switch is going to start acting like a hub by flooding all of the new frames like broadcasts. So one of the ways that we can protect against that is to implement either routing in the network or to implement some other flood control mechanisms. But we don't typically want flood control mechanisms to protect normal operations. We're looking at flood control mechanisms to protect against denial of service attacks and other types of attacks on the network. So if I come in here and I go into global configuration mode, I just simply have to say MAC address table aging time, and I can change it to 600. And that's very simple. It just changes on the fly. Any of the MAC addresses that were already learned are still going to stay in the database, but we've just extended that time in the database itself. So just to recap, as part of this process, as part of what we were discussing in this particular discovery, is that the MAC address table contains address information that the switch uses to forward traffic between ports. All MAC addresses in the address table get associated with probably one port, maybe more ports. The address table includes a couple of different entries, and we haven't looked at the static element of this yet, but it certainly includes dynamic entries where the source MAC address is learned and then ages out when it's not in use, like we talked about. There's also manually created entries that we can use as well that don't age out, and they're not even lost when the switch resets. We would see something like that if we were doing, say, port security, for example. The address table lists all the destination MAC addresses, the associated VLAN ID, the port numbers that are associated with the addresses, and then obviously how we learned that particular address, whether it was static or dynamic. Believe it or not, there's actually a way that you can disable MAC address learning on a particular interface or on a VLAN. By default, obviously MAC address learning is enabled on all of the interfaces and all the VLANs on the device. We can control MAC address learning on an interface or on a VLAN to manage the available MAC address table space by controlling which interfaces or VLANs can actually learn those particular MAC addresses. Obviously, you need to make sure about your network topology and what the impact of making that change would be, because we could potentially cause flooding in the network if we do that. So Cisco does recommend, obviously, use caution if you're going to do this. You can actually disable MAC address learning on a single VLAN, anywhere from 1 to 4094. The command is basically just no MAC, let me get back over here, no MAC address table learning, and then I can specify, well, that should be the command, no MAC address table. This switch might not have that capability. What you should be able to do, and maybe it's a switch specific, but the command would be no MAC address table learning, and then you could specify the VLAN, whether it's an individual VLAN or whether it's a range of VLANs and so on. All right. The only time that you would ever really want to disable MAC address learning on a VLAN is if that VLAN only has 2 ports, and then every frame would then get flooded, but it would be like normal traffic in that particular case. We can't disable MAC address learning on a VLAN that is used internally by the switch. That is something that I'm going to talk about in another exercise. There's a VLAN internal usage option that we have when we create routed interfaces on a multi-layer switch, and we'll talk about that later on. All right. So this was just a basic introduction to the concept of how the CAM table is learned. There's a couple of other commands that you could run, for example, let me just do a show MAC address table. Let's get out of config mode. Show MAC address table. And if I use the question mark, we can see things like count. The count displays the total of number of MAC addresses that are present in the table on a particular VLAN. Dynamic will show only the dynamic entries. Interface shows only the specific MAC addresses for an interface. Show MAC address table learning. That's going to show you the learning status of the VLANs. We don't have that here because we don't have the option of disabling that in this particular iOS. Show MAC address table static, and then we can also do show MAC address table VLAN if we want to see a MAC address on a per VLAN basis. All right, so we'll wrap up this particular very short discovery, and we'll see you guys in the next one in the next couple of lessons. All right, so in our next section, we're going to talk about the difference between what happens at the control plane and what happens at the data plane. Now, generally speaking, there are three planes of existence in most Cisco devices: the control plane, the data plane, and the management plane. The control plane is the higher level functions of the device. The CPU processed functions like routing protocols run at the control plane. The TTLs get decremented at the control plane. CRC checks and whatnot, checksums get verified at the control plane. The data plane is the interface level, right, where data enters and exits the device at the interface level. And then the management plane is what we use to manage the device. SSH sessions, Telnet sessions, SNMP sessions, etc. Those are going to communicate to the management plane. And we're going to be talking about later on in our security section, how do we protect the control plane, being that that is the plane that allows us to process critical information. That's going to be a very important component to protect. It's not the goal of this particular section here. We just want to differentiate what one is versus the other. So think of the control plane, even though it says routing protocols and IP routing happens at the control plane. It doesn't, I mean, obviously on our switches we're not running routing, but there are still CPU functions that get processed. In basic frame forwarding, there shouldn't really be any control plane traffic, but any kind of action that the switch is going to have to take, like doing a CRC calculation check or a frame check sequence check, or manipulating a frame in some way, doing some sort of frame rewrite if I'm doing routing between SVIs on the switch or something like that, that's going to require some sort of control plane function. It says here that a layer 3 device employs this distributed architecture, but we would see this typically in other types of devices as well. The control plane code, that's going to be anything that runs on the route processor, and then the switching fabric itself, the ingress and egress ports of the device, that is our data plane function. Now, why do we differentiate this? Well, we would like to maybe maintain all the traffic flow at the data plane. In other words, come up with a mechanism that allows us to take control plane information, cache that control plane information, and then use that cached information to be able to make data plane processing decisions and avoid ever using or sending traffic up to the control plane. Because processing things in hardware is always going to be far more efficient than processing things in software. And that's really the idea, right? We want to make sure that we process things as quickly as possible. All right. Now, there are specific actions that are the main function of the control layer and the function of the data plane microcode that exists within that data plane itself. The bullet points there, the 4 bullet points: managing the internal data and control circuits for the packet forwarding and control functions. That would be a function of the control plane. Extracting the other routing and packet forwarding related control information from a layer 2 and layer 3 bridging information, and routing protocols and the configuration data, and then conveying that information to the interface module for the control of the data plane. So in essence, what they're saying there is, I'm going to take information that is collected and maintained at the control plane. I'm going to extract the pertinent information that allows me to make forwarding decisions, and I'm going to cache that information at the data plane so that I can then use the data plane to make actual processing decisions, right? So collecting data plane information, traffic statistics from the interface, and then sending that to the route processor, handling certain data packets that are sent from Ethernet interface modules to the route processor. So there are exceptions to data plane processing. If, for example, the time to live is going to be decremented to 0 and we're going to not be able to route a packet, for example, that is going to be an exception. All of this caching, all of the way that we process this information, the way it gets processed and sent, or the caches get built, is through a method called Cisco Express Forwarding, and that's obviously what we're going to be talking about next. All right, where is the exchange of routing information performed in a layer 3 device? Well, that's going to be at the control plane. All right, that means the hello packets that we have, the the adjacency information that gets exchanged between routers, that happens at the control plane. Okay. Now I mentioned this briefly. Actually, I mentioned I referenced different switching methods previously. And I want to mention that again here because even though that's not really what this particular slide is about or this particular section is about, but there are different ways that switches can process information. Now they talk about process switching versus fast switching versus Cisco Express Forwarding, which is topology-based switching. We'll talk about that in a minute, but I also want to talk about the 3 different overall switching methods that a switch has. One is called store and forward. All right. Now, if you were to look at an Ethernet frame, in fact, let me go ahead and pull that up real quick and show you. If you were to look at an Ethernet frame and look at the structure of an Ethernet frame, it basically has, in essence, 4 components, right? You've got the destination MAC address, the source MAC address, Ethernet to frame format, the type field, the data field, and the frame check sequence, right? So ultimately, when you look at a frame, view image, this is what the frame looks like. That's not a very good image here. Let's get a better one. Let's do this. Tools, size, large, and really? Oh, there we go. Perfect. Wow. I'll just go right here. I'm surprised it's so small. That's why it's not letting me expand that. All right. So on the top here, we see an Ethernet 2 frame. That's the DICS Consortium, Digital, IBM, and Xerox came up with this format, which we still use today, by the way. We use it actually pretty much for every kind of communication that's client-based. And then we have the 802.3 frame format, which is used primarily for switch-to-switch communication like CDP or LLDP or DTP and so on, right? But if you look at the frame, forget the preamble, the start of frame delimiter. Those are really just synchronization and timing bits that are used to identify that a frame is coming. Doesn't actually contain any real information. The first field that actually gets processed that contains real information is this destination address field. And this, of course, is the destination MAC address. Now, switches make their decision based on that MAC address. right? I mean, that's how we ultimately make a forwarding decision. They build the database based on the source MAC address, but they make their forwarding decision based on the destination address. So technically, all the switch needs to see is the first 6 bytes of a frame to make a forwarding decision. We can actually set that up on a Cisco device to do that. We can actually go into the Cisco device and say, I want to do cut-through switching. Cut-through switching is where you process the first 6 bytes of the frame and you start forwarding the frame after you've read the destination address. It is certainly going to be the fastest switching method, right? It's the fastest switching method because I've already started forwarding the frame after only receiving the first 6 bytes. But the downside with cut-through switching is you might run into a situation where you start forwarding fragments and invalid frames. Another switching method, which is what a lot of devices employ by default, Cisco doesn't, but other devices do, is called store and forward switching. Any idea what store and forward switching is? Well, it is the process of processing the entire frame, including the frame check sequence, before I start forwarding the frame. Store, S-T-O-R-E, store and forward, right? So this is the slowest switching method, but the benefit of this particular switching method is that you will never forward an invalid frame because you've stored the entire frame. You're able to do the frame check sequence, the cyclic redundancy check, and verify the integrity of the frame by doing your CRC, and then you can start forwarding the frame. Cisco actually employs kind of a combination of both of these. It's called fragment-free switching, right? And with fragment-free switching, we process, in essence, the critical part of the frame. I believe it's the first 64 bytes. Let me make sure. I think it's the first 64 bytes. Verify this. Cut through. Where's fragment free? Yeah, first 64 bytes. All right. So what it does is it processes the first 64 bytes of the frame, which means that most likely it's not a fragment, because fragmentation typically occurs in the beginning of the frame. So it's most likely not a fragment, which means it's most likely probably a legitimate frame. And we can process that frame and without having to go and store the entire frame and send it through. So I wanted to talk about that before we got into this piece here. This is kind of unrelated. I don't recall whether or not they actually have a discussion about the store and forward, the fragment free, or the cut through switching, but I did want to mention it anyway. All right. Now, with regard to actually processing data through the different planes of existence, the control plane versus the data plane, the slowest method, and in a lot of devices, the only method that's available, is to do process switching. Basically, process switching means that every single piece of data that goes through the device has to go through the CPU. And we have to switch that traffic through the CPU. Even though it's part of a flow of traffic that already exists, that we've already identified, we have no caching mechanism built into the device to be able to cache that information, so we simply do what we call process switching. All right? Certainly the slowest method of switching. The next best thing would be to do fast switching. And fast switching is essentially a process in which we cache information. So the first packet, or the first PDU that's part of the data flow, part of the flow itself, gets process switched. And then based on that information, we build the caches, the adjacency cache, the forwarding information based cache, and so on. There's typically 2 different caches that are created with this caching mechanism. And then each additional subsequent packet within the flow is going to be switched at the data plane using those caches rather than being processed at the control plane. This is not Cisco Express forwarding, right? It's very similar to Cisco Express forwarding in that the caches get built, but with Cisco Express forwarding, what we call topology-based switching, what happens is the caches are pre-built even before the first flow happens. So you can see there that we have two different databases that are built. This is related to a test question. A forwarding information base, which is essentially a cache of my routing table, and an adjacency table, which is basically a cache of my exit interface and next hop MAC address, etc., that I would need to have available to do my frame rewrites and so on as the data moves through the data plane. All right. So this topology-based switching mechanism is certainly going to be the fastest because the hardware caches, the caches that are built in our ASICs, are going to be built regardless of traffic flows. But there are some limitations to this particular method. Especially when it comes to load balancing, Cisco Express forwarding tends to break load balancing unless you have a large number of flows. You're going to get some sort of kind of irregular load balancing. There's a term they use to describe it. I'm trying to think of it right now. Polarization is what it's called. You get some polarization on a particular interface or so on. We'll probably see that a little bit later on when we get into some of our load balancing tools. All right, so Cisco Express forwarding is turned on by default. It's going to be a lot less CPU intensive even than fast switching because, again, we're building the caches even before the first flow goes through the device, right? The ARP cache, the ARP cache, which allows us to map MAC addresses, destination MAC addresses to destination IP addresses. If you think about how routing works, right? There are three major components to routing. Where you're trying to get to, and how you get there, which is broken up into two parts, right? The exit interface that you go out of, the next hop address, which would include the layer 3 and the layer 2 address, if it happens to be a kind of a broadcast type of network. So we're going to take that information that's normally built by the CPU, and we're going to build out our hardware-based tables called the forwarding information base and the adjacency table. Those tables then are going to be used to make any of our subsequent forwarding decisions, even for the very first frame that comes through the device. All right. They mention here, for example, in kind of the last part of this first paragraph, some features are not compatible with Cisco Express forwarding. There are some instances in which Cisco Express forwarding can downgrade performance, and that happens particularly when it comes to load balancing multiple paths with a routing protocol. Oftentimes the load balancing mechanism that a router uses is completely different than the load balancing method that Cisco Express forwarding chooses. And that's where that polarization comes into play. A polarization is when one link is going to be utilized more than other links based on the decisions that Ceph is making. This is probably something that we'll demonstrate a little bit later on when we get into some load balancing scenarios. I'll show you guys how that looks and how we can kind of work around that, if we will. Polarization becomes a lot less of an issue if you have lots and lots of unique flows. Cisco Express forwarding loves to do load balancing based on unique flows. And we can modify that load balancing method, just like we can modify, say, an Ether channel load balancing method or routing protocol load balancing method. All right. So EIGRP, we'll say we're running EIGRP in this particular case. A couple of the data structures that are built are the topology table. The topology table in EIGRP is everything that I'm learning. So, you know, who's the advertising router for a particular prefix? What is that next hop IP address? And then I can use that information to identify what egress interface that particular neighbor is tied to. I can use the neighbor table for that, or I can actually use my routing table. Remember, the topology table is different than the routing table. Right? Topology table is everything that I know. The routing table is everything that I'm using. So we don't really route with the topology table. We choose to route with the routing table, but that is what we call our EIGRP RIB, routing information base. So you'll see that term used quite often. This second table here is the RIB. Excuse me. This topology table is the EIGRP RIB. This routing table is the global RIB. All right? Because again, the routing table is not specific to EIGRP. I'll have my local routes in there. I'll have my connected routes in there. EIGRP, OSPF, whatever. That is my global RIB, my global routing information base. The topology table is the routing table specific to EIGRP. So it would be my EIGRP RIB. Just like I would have if I did a show IP BGP, that would be my BGP RIB. Show IP OSPF database would be my OSPF RIB, and so on. All right? Or at least contains information about that. So I take this information, this is all control plane information, and then I build my fast switching cache. This is the destination prefix. This is what the layer 2 header is going to look like after the rewrite. This is the interface it's going to go out of. And I don't have to worry about going up to the control plane and looking at those other databases. All right? So let's go through a specific scenario here. There's a sequence of events that occurs when where process switching and fast switching are used for the process. Now with process switching, it's very simple, right? No caches are built. Everything is sent and controlled at the control plane. So in that case, we don't have any fast switching caches that are built. So that's pretty simple. Fast switching, as we know, the first packet is going to be, and the flow is going to be process switched, and then the remaining packets are going to be fast switched. So EIGRP gets its updates. We process that information. We create our topology database. We, of course, have our adjacency database prior to that with all of our neighbor information. We learn our routes from our neighbors. That becomes our topology database. And then when the first packet arrives for a particular destination, we try to find that information in the fast switching cache. Because we haven't built the fast switching cache at this point, we process switch that packet and we do our recursive lookup. Remember, routing is always about recursion. Unless the route is directly connected, there's always going to be a two lookup process, right? The first lookup is what is the next hop for a particular destination prefix, and then the second lookup is what connected route is that next hop tied to. So that's the recursion that they're referring to. One is a network route that allows us to identify a particular network destination, and the next one is the actual connected route. All right. Let's see. And finally, then, once we've processed that packet and we trigger kind of the whole routing process, that's when we create that entry in the fast switching cache, and then all subsequent datagrams that are part of that flow are going to be fast switched. All right. So it says here now the switching occurs in the interrupt code, meaning that it's processed in hardware. The fast destination lookup is performed, meaning we go to the fast switching cache. We don't have to do any recursion. And then the encapsulation is generated based on the information that's stored in the fast switching cache. So we're not doing an ARP request. We're not waiting for an ARP reply, etc. All right. If a router receives a packet that should be fast switched, but the destination is not in the switching cache, we'll go ahead and process switch that datagram and we'll create the fast switching cache. So the only difference between fast switching and Cisco Express forwarding is that with Cisco Express forwarding, the caches are generated and built before the router sees any particular data flow. So initially the router converges, we get our topology information, we get our routing table. We then automatically take that routing information and we build our forwarding information base, which is called the Ceph cache, and our adjacency table, which is basically next hop to MAC address bindings, so we don't have to do ARP requests and so on. All that stuff is built automatically. A lot of arrows here, but basically all they're saying here is we're extracting information from one database that was created at the control plane, and we're creating these caches at the data plane. All right. So we separate the control plane from the data plane, which ultimately should allow for faster throughput. That's the goal. And that control plane is what's responsible for building those routing information bases, which then in turn become the forwarding information bases and the adjacency table. So two databases that get built, a forwarding information base and an adjacency table. All right. As I mentioned, OSPF, EIGRP, BGP, ISIS, they're all going to have their own routing information bases. Most often we simply refer to those as the topology tables for each of those protocols. Even RIP has its own routing information base. If you do a show IP RIP database, you can see that. In OSPF, it's show IP OSPF database. In EIGRP, it's show IP EIGRP topology. And so on. In BGP, it's just show IP BGP. So there's ways to see that specific protocol's routing information base. That information, like I said, gets extracted and it goes into the global RIB. The global RIB is basically your routing table. All right. That forwarding information base, which is our layer 2 cache, gets derived from the global RIB. It is arranged in a very particular order so that we have maximum or speed with regard to lookups, and then the information is all stored in a ternary content addressable memory table from the most specific entry to the least specific entry. So remember, we always do longest match routing first. So a 10.0.0.0/24 route will go before a 10.0.0.0/16 route because we're going to prefer the /24 route over the /16 route as long as the packet matches the route. Okay? So it makes sense, right? All these caches are built, and then that allows us to do our layer 2 forwarding. Now, there are exceptions to packets that simply cannot be Cisco Express forwarded, right? If you have options within an IP header. One of the fields, the IP header is pretty basic, right? It's got a version field, it's got a header length field, you've got your toss byte or your QoS field, you've got your total length field, you got your fragment offset flags and identification fields. You've got your, what's after that? Time to live, your protocol field, checksum, source IP, destination IP, and then finally you have your options, right? So a packet with options has to be process switched and can't be fast switched. If the TTL is expiring, I mentioned that before, that means the packet can't be routed, so the control plane is going to have to respond with some sort of ICMP TTL exceeded message to the sender. If you're sending traffic to a tunnel interface, so it's going to have to be encapsulated in an IP, another IP header or a GRE header, whatever, that's going to require control plane processing, obviously. If they arrive with an unsupported encapsulation type, in other words, maybe it's a malformed frame or it's misencapsulated, or if they exceed the MTU, right? So that's when packet fragmentation has to occur, or if the DF bit in the packet header, that's one of the bits in the flag field. There's only 2 bits in the flag fields that are actually used, the DF and the more fragments. DF is do not fragment, and the more fragment flag means that fragmentation is occurring and there's more fragments within the flow. But the idea is that that's, again, those are kind of options that are are part of the packet header. So those packets would not be Cisco Express forwarded. All right. Which of the following Cisco switching mechanisms is the default on Cisco routers? Well, it would be that. And you can actually go into a device. You guys are going to be doing the exercise here, but you can go into a device and you can disable Ceph just by using the global command no IP Ceph. Or you can enable Ceph by typing the command IP Ceph. There are rare instances where you may want to disable Ceph globally on the device. You can also disable it on some platforms on a per interface basis, but for the most part we will disable it globally. All right. All right, guys, welcome to our second discovery in ENCOR, CCNP ENCOR. In this discovery, we're going to take a look at Cisco Express forwarding. We've already gone through, of course, the lecture where we talk about what the benefit of Ceph is and how it works in our routed environment, but now we're going to inspect both the forwarding information base and the adjacency table, and we're going to see how their contents update to reflect the changes that happen in the control plane. We're also going to learn how to, in this particular lab, enable and disable Cisco Express forwarding on specific devices. So on the HQ router, we're going to verify our FIB, we're going to verify our adjacency tables, we're actually going to set up some EIGRP to trigger some updates and to generate some additional traffic for the overall architecture. So before we do any of those changes, before we actually start to add additional routes and whatnot to the network, let's go ahead and go into the HQ router and take a look at the Ceph table. So we're going to do a quick show IP Ceph. And what you're going to see in this case are really just the information that is specific to this particular router prior to learning anything in the network. So without EIGRP, we're seeing a default route. It says there is no default route in this particular case. So this 0.0.0.0/8 we're going to drop because we're not going to accept any packets that start with 0. We can see we're going to receive routes, any route from anybody on any interface. And we have a couple of interfaces here that are configured, right? This is the prefix that's on the gig 00 interface. This is the network ID, if you will, for that particular interface. Or this indicates, obviously, that we're going to be able to receive routes on that interface. This is the physical IP address of the interface. This is the broadcast address of the interface. So we're seeing all the characteristics of the physical interface that's active on this particular router. We're also going to drop any traffic that we receive to the loopback interface. Presently, we're going to drop all traffic that we receive to a 224 address. That might change, by the way, when we enable EIGRP, because EIGRP uses multicast. And we're going to drop the experimental range as well, which is the class E space. And then all ones broadcasts we're going to go ahead and receive as well. So if I do a quick show adjacency, well, I don't see presently any adjacencies in the database. These are my layer 2 adjacencies because I haven't gone through any specific ARP request, right? There's an entry in the FIB table for every network that we know about, for every entry in the routing table. So that would be my connected routes, my local routes, and those get automatically pre-configured into the FIB. But because HQ is not really running any routing protocol, only those local networks are going to be present in the routing table. So router HQ has no information about the remote network that we have in our topology, which is 192.168.110.0/24. The adjacency table, as you can see here, also doesn't contain any entries because that adjacency table is actually built from the ARP cache, the address resolution protocol process. Because we haven't generated any traffic yet, there aren't going to be any entries in the ARP cache, and so the adjacency table is going to be empty. So we're going to go ahead and initiate some traffic on HQ towards the neighboring router. The neighboring router's IP address is 10.10.10.2. So let's go ahead and do a ping to 10.10.10.2. Now the first ping will probably fail. We'll get some packet loss because the router was waiting for the ARP reply from BR1, which had to complete before we could actually fill out that ARP cache with that appropriate information. Now if I do a show adjacency, I should see an adjacency listed in the database, and sure enough, I see that. In fact, if I also do a show IP Ceph, I should also see information about the 10.10.10.2 address, which is the peer address. And notice it says that that network or that IP address is attached to gig 00, indicating that we learned that through a discovery process. All right, so the adjacency table has changed. We learned about the new end host through the ARP process, and so the entry is created in the fib table. So now what we're going to do is we're going to turn on EIGRP on our HQ router. BR1 is already configured with EIGRP, so we should just see an adjacency come up. We happen to be using EIGRP autonomous system number 1. So I'm just going to go in here and say EIGRP1, and I'm going to specify network quad 0, and I should see the adjacency come up. Yep, sure enough, I see my adjacency come up. So now we're generating EIGRP traffic back and forth in the form of hellos and updates and acknowledgments and so on. If I look at my routing table, I should see a route, show IP route. Sorry about that. I had a couple of interfaces that were still disabled in my platform. When you're using the viral stuff, or in this case iOS V, the interfaces are turned off by default, and I just simply forgot to turn on those interfaces. So those networks were not advertised. But now, if I do a show IP route, I should see that route in the database. And in fact, my Ceph information should be quite significant as well. I mean, we should see that we're now participating in some other attached interfaces like gig 01. All right, so we see the interfaces are up. We see the routing table or the route in the routing table as learned via EIGRP. So if I go ahead and I look at my adjacency or my fib table again, I can see the 192.168.110.0 subnet, which is right here. And notice that we've identified the next hop as 10.10.10.2, which is going to recurse to this attached connected route, if you will. So if you think about how routing works in general, dynamically learned prefixes or network prefixes that we learn from other network routing protocols are going to recurse to some sort of connected interface, or some sort of local interface where I have to go out of to reach the next hop to reach that particular destination. If I do a show adjacency, again, we can see that we actually see the 10.10.10.2 address is tied to the gigabit 00 interface. So now that the fib table has a new entry for that 192.168.110.0 subnet, the new entry is there, obviously, because the routing table changed and the new route was learned through EIGRP. On the other hand, the adjacency table didn't really change, right? Because ARP didn't change. We don't really do a resolution for external networks or external destinations. Now, how do we verify that Cisco Express Forwarding is actually enabled on an interface? I use the command show IP interface gigabit 00. And specifically in this output, what I'm looking for is the IP Ceph switching is enabled. And we can see that here. It is turned on by default in Cisco devices. So this IP Ceph switching is enabled is in the output. That tells us that Cisco Express Forwarding has been enabled on the interface. Ceph is enabled by default on all of the interfaces, actually, with the global level command IP Ceph. Now, you should use Ceph whenever possible, but there are instances where you may have to disable Ceph when you experience issues like choosing an appropriate interface, or maybe load sharing and load balancing with an IGP protocol is not working correctly. You may have to disable Ceph to achieve better results. But generally speaking, it's not something you would normally turn off. Now, Cisco Express Forwarding for IPv6, on the other hand, that is not enabled by default, but it is enabled when you decide to enable IPv6 unicast routing on your devices. So if I come into my router here, for example, and I do a show IPv6 Ceph, we can see it's not running, but if I come into the interface or into the router and I say IPv6 unicast routing, do show IPv6 Ceph, we can see now that it's enabled. So it's not really enabled by default because we really don't have IPv6 enabled by default. So as soon as I enable IPv6 unicast routing, it does turn that feature on. All right. How do we disable Cisco Express forwarding on a per interface basis if you do in fact have to do that? Now, here's a couple of things that we consider, right? Even though Ceph does technically support load balancing, the disabling of Ceph because load balancing isn't supported, maybe there's poor performance, or there's adverse, Ceph is adversely affecting the performance of the device, we may choose to disable it. One of the later lessons that we're going to get into, we'll talk about how Ceph actually breaks load balancing, and that is something that we obviously want to be aware of. Now, when I say it breaks load balancing, it just uses a completely different method. We do per flow load balancing with Ceph as opposed to per packet load balancing with most of our IGP routing protocols. So if I want to disable Ceph on my gig interface, I simply go into interface gig 00 and I say no IP route cache Ceph, and that disables Ceph on a per interface basis. If I go in and I do now a, let's do a do show IP interface gig 00, and let's pipe include Ceph, we can see IP Ceph switching is now disabled on that particular interface. All right, if I want to disable Ceph globally on a platform, I simply have to go into the platform and go into global configuration mode and type no IP Ceph, and that will disable Ceph globally on the platform. Again, not generally recommended, but there may be special cases in where you have to do something like this. Now, before we wrap up this lesson, I want to talk a little bit more about some other aspects of Ceph outside of what we learned in the lesson, and then we'll wrap up this exercise and get on to our next discussion. Now, when we talked about Ceph as part of our lecture, we talked about it as almost a proprietary form of scalable switching, right? The idea is that we're trying to tackle the problems associated with on-demand caching. So with Cisco Express forwarding, this information, which normally is stored in a route cache, gets split up over different data structures. And we talked about those data structures as part of our process. In fact, we looked at them in this particular case, right? The forwarding information base, which allows us to make IP destination prefix-based decisions much faster. Basically, it's similar to a routing table. It maintains a mirror image of that forwarding information that's contained in the routing table. And even when we saw this in our exercise here, when the routing table topology or the routing or topology tables change, the routing tables update, and those changes are going to be reflected in the FIB. The FIB also maintains next hop address information based on information that's stored in the routing table as well. Because there is a one-to-one correlation between the FIB entries and the routing table entries, the FIB actually contains all known routes and eliminates the need for route cache maintenance that gets associated with different switching paths like fast switching, which we talked about in the lecture. Now, the adjacency table allows us to identify nodes in a network. Those nodes are said to be adjacent if we can reach each other with a single hop across a link layer, like a data link layer connection. So the Ceph uses the adjacency table to prepend layer 2 addressing information, which maps layer 2 next hop addresses for all the different FIB entries. Now, the last thing I'll talk about before we wrap up this lesson is there are a couple of different modes of operation of Ceph depending on what type of platform you have. We didn't really talk about this in our lecture portion, so I wanted to make mention of this before we wrapped up. There is what we call central Ceph mode and distributed Ceph mode, or what we call dCeph. If we're using Ceph on the device, the Ceph FIB and adjacency tables go in the route processor, and then the route processor performs the express forwarding. We can use Ceph mode when we have line cards, well, actually, I should say really when line cards are not available or don't support the Ceph switching function, or when we have to have features that are not necessarily compatible with the distributed Ceph model. With a distributed Ceph model, the line cards maintain identical copies of the fib and adjacency tables. Those line cards are actually the cards that go into the various slots on the device. And the line cards themselves perform the express forwarding, relieving that gigabit route processor or the general route processor from involvement in the switching operation. This is the kind of stuff that you're going to see on routers like 12,000 series routers or 6500 series routers that have individual line cards and distributed processing. So you might see a command that indicates that Ceph is distributed across different devices. All right, so we'll take a look at this more later on when we get into some of our advanced routing topics and we start to talk about how Ceph affects general routing decisions. Now, one of the things that I wanted to point out here as well as part of our discussion is that there is a there are several documents actually that exist out there. Let me pull this up real quick. That if you just go out and Google Cisco Express Forwarding breaks load balancing, you'll see multiple documents that describe how Ceph creates a polarization problem or how Ceph creates issues when we're using traditional load balancing over parallel links with routing protocol. So I would say definitely go and take a look at those documents. This one is very useful actually, troubleshooting load balancing over parallel links if we're using Cisco Express Forwarding. And it discusses really what the issue is with Cisco Express Forwarding and how the load balancing mechanisms work with traditional routing protocols versus how they work with Cisco Express Forwarding. So we'll wrap up this lesson here and we'll see you guys in the next discovery in our next section. So let's go ahead and wrap up this lesson here. Which of the following commands will allow the administrator to view which MAC address table is mapped to which port? Show MAC address table. By the way, the command does vary. I believe this is going to be the right answer in this case. Sometimes there's a dash between all of the keywords, and sometimes there's only a dash between address and table. I've seen that. It depends on the platform. Some of the older platforms has a dash between all three keywords, MAC, address, and table. Some of them only have the dash between address and table. Which of the following tables is used to make the decision on whether a frame should even be forwarded based on the frame being permitted in an ACL? All right, well, ACL information is going to be stored in the Tcam. Remember, we have a Tcam that stores QoS information as well as access list control information. On a Cisco router, which of the following two actions are functions of the control layer between the routing protocol and the firmware data plane microcode? Management access would be the management plane, not the control plane. Managing the internal data and control circuits for packet forwarding. Forwarding the packets would be a function of the data plane. Collecting data plane information like statistics from the interface to the route processor. That would definitely be a function of the control plane, collecting that information for the purposes of monitoring. So we have a choice. Is it either managing the internal data and control circuits for packet forwarding and control functions, or verifying the interface status? It's going to be managing the internal data and control circuits for packet forwarding, because the interface status is tied directly to that interface, which is going to be a data plane function. All right. All right. Which one of the following options is the default switching mode and uses information from tables that are built by the CPU, such as a routing table and the address resolution protocol table, to build hardware-based tables that are known as the fib and the adjacency table? That would be Cisco Express Forwarding. What is the default aging time in seconds on a Catalyst switch? That would be 300 seconds or 5 minutes. Which of the following Cisco switching mechanisms require a Cisco router to process all packets in the CPU? That is process switching. It takes a large, it takes an involved process to process the information, or we're sending the data to the processor. So that would be process switching. Which of the following Cisco IOS router commands would disable Ceph on a specific interface? No IP route cache Ceph, but make sure that's an interface command, not a global command. Which of the following commands would allow you to verify Ceph is enabled on the gig interface? All right, show interface, show IP interface gig 00. We don't reference Ceph specifically in either case, and we don't reference Ceph from the show IP interface command. Which of the following commands can be used to set the aging time? MAC address table aging time, right? And then we specify the time in seconds. And we did that as part of our lab exercise. All right, which of the following commands would allow an administrator to view which MAC addresses are mapped to a port? Well, we could certainly use show MAC address table. Oh, these are the repeat ones. I don't know why they do that. All right, so we'll skip all those. We already did all those. All right. So that wraps up this lesson. We will see you guys in the next lesson.